Hello everyone. In this video, we will learn what is a counting tree and how we can use it to solve some counting problems. Well, we have already worked with trees, but counting tree is a special one. So counting tree is a label. Counting tree is a labeled tree. Well, it's a labeled tree, and there are some rules for labeling its edges and points. So points labeling rules. So first thing is that the root is labeled by a number. The root is labeled by the total number of elements in the universal set. But any other point is a name of a set. So every is labeled, every other point will be labeled, is labeled by a set name. Well, what kind of sets? There is a rule on that. So if you have outcoming edges of from one point, you have to label this endpoints with something A, B, C, D, such that these sets is a partition. So the sets is called partition. Partition. What does partition mean? Partition mean that they have 2 by 2 mutual empty set, so they don't intersect. And if you find the union of them, it will form the universal set. So A union B union C union D, for any point this should work. This must be equal to universal set, and they're mutually exclusive. It means that any two of them, if you look at their intersection, they don't intersect. Their intersection is empty. Okay? How about labeling of the edges? So edge labeling rules. Well, there is only one rule. All the edges are going to be labeled by one number. So every edge is labeled by a number. What number? This is number of elements of a set. What set? Which set? So you look at this edge, you find the endpoint. Endpoint is the point on the right hand side. So from that point to the root, there is only one path. So find all the sets on the path from the endpoint of that edge to the root. So you basically go from the end point of that to the root, and along the way, whatever you see, you set intersection of those ones. That is intersection. And when you find all this intersection, find the number that will give you the label for the edge. Okay, let me show you how does this work. So let's say I have the first comes out A. Well, one of the best partitions is that when you take A, you take for the other point when there are two A complement. Then you go, for example, B. I can have B complement here. Then I can have a partition here, C, D, and then A, B, C, D, E, sorry. And then I have, for example, I can have this and that. Okay. Now, for the origin, I will use, for the root, I will use the number of elements in the universal set. For the first edge, I will use NA, because from the end point to the root, there's only A. For this edge, I will use NA complement, because there's only one, this one. For this one, okay, so I start from here, go there to the root. I saw A and B, so find their intersection, then find the number of elements. That's the label for that edge. For this other one, let's say for this one, okay, for this one here, for this edge, I go to the endpoint. This is the endpoint, and find the path from that to the root. So I have to go that way, yes. Then along the way, I saw what sets I saw. I saw A, I saw B complement, and I saw F. Then N of that is what you put there. For this other one down there, I can, you can see that I have N, A, B, C, and then F, C. How about here? This will be N of A, C intersect C. This will be N of A complement intersect D. This is N, A complement intersect E. So those, all those labels, now this is a counting tree that we can use to find our numbers. There is one thing that will come as a result of the way we set up the labeling. As a result, this is the simplest thing that you will see. You consider any edge, any point that you see. There are some edges that go out of that edge. So on the right hand side of that node, there will be edges that going out. So sum of all the labels on the outgoing edges must be equal to the number on the incoming edge. This is a result of choosing these sets to be a partition. Okay, so they say that, what does it say? It says that you see these numbers 1, 2, 3. These are outgoing numbers on the outgoing edges of this point here. This is incoming. So this one must be equal to the sum of those three numbers. Let's see this in some examples and you will notice what I mean, but these are the rules that we will use all the time. Okay, we have a counting tree. Some of the numbers are there, some are not. We are supposed to complete this, meaning that put all the numbers that are missing. Okay, so right away you notice that, okay, NU here is 150, yes, that's the root. Now, from 150, there's a number 90 in one of the outgoings, but the other outgoing has nothing yet. These two must add up to 150. So that is telling me that 150 minus 90 will be the label of that edge. And the same argument can be given here. you see that the incoming is 90, outcoming there's only one number and one of them is 50 now, sorry, 20. So that means that here the label must be 90, whatever is left out, that's 70. And I can use the same argument here, 70 minus 15, this must be 55. Here 10 of that gone there, so the rest should go there. Here's funny thing, so this and that are two labels of outgoing edges from A, so they must add up to the number back here. So this must be 8 plus 2, which is 10. Now that I know 10 is there, the incoming is 60, so this must be 60 minus 10, which is 50. 50, there are 6 of them down there, so 50 minus 6, this must go